Hello everyone, today I'm going to walk you through the Getting Started section of our Dyad documentation. As you can see here, the webpage I'm starting on is help.juliahub.com/dyad. So what I'll do from here is select the Getting Started button at the very top. And this is what we'll be walking through today, getting started with Dyad Studio. However, if you haven't done so already, make sure you visit the installation page right here. And on this page, I'll walk you through how you can create a JuliaHub account, how you can install the Julia programming language, install Visual Studio Code, as well as the Dyad Studio extension. And once you've done that, you'll be ready to move on with the Getting Started section. So here, what we'll be showing you is how you can use the Dyad VS Code extension, how to create a Dyad model, compile that model for simulation, run basic simulations, as well as how we can bring in standard libraries and compose models from components. So what I'm going to do is I'm just going to walk through each of these steps one at a time. I recommend that you have this web page open as you follow along. So here I am. I have a VS Code window open. What we're going to want to do is go ahead and create our first Dyad component library. So what we're going to do here is we're going to open up the command palette like so. If you're on a Windows, you can hit the keys Control-Shift-P. If you're on a Mac, you can hit the keys Command-Shift-P. So here, once the command palette is open, you're going to want to type out Dyad and select Create Component Library. Here, it's going to prompt you to give your component library a name. We recommend that library names end in components, just so you can easily remember which libraries contain components, but that is not a requirement. I'll go ahead and name my library Demo Components and hit enter. Once I do that, it's a Explorer window is going to open up and it's going to ask me where I want to save my component library. So I'm going to go ahead and go to my desktop, and I've created a folder where I want my library to be saved. I just named that folder Dyad Components. So I'm just going to select that folder and hit the select folder button right down here. Okay, once you've done that, you can see a new VS Code window has opened to my demo components folder. So here it's asking me if I want to activate a different environment. You can go ahead and just ignore that. So from here, you can see that your library has been populated with a few different files and a few different folders containing other files. For now, don't worry too much about that right now, but this is all the artifacts needed to properly configure your component library. So let's go ahead and set up our environment and test our environment just to make sure everything's working as expected. What we're going to do here is, once again, open up the command palette. And what we want to do is start up a Julia session, a Julia REPL. So go ahead and type out Julia and select Julia Start REPL. At the bottom here, we can see a Julia session has started. So what we're going to want to do from here is we're going to want to enter the Julia Package Manager. And in order to enter the Julia Package Manager, right here in the REPL, you're going to want to hit the close bracket key, the close bracket key. And the close bracket key, of course, looks like this. So you're just going to want to hit that key right down here in the REPL. I'll go ahead and do that right now. And you can see that I am now in the package manager, and it's indicating that my environment is the demo components environment. So go ahead and type out instantiate to instantiate our environment. Some of these steps may take a few minutes to complete the first time, because what's going on is all the nearly or approximately 500 individual packages in the Dyad ecosystem are being compiled for your machine the first time you load them in a project. So this is a one-time cost, and subsequent loads of this project will be much faster. Okay, it looks like everything is successfully pre-compiled. So back down here in the package manager, go ahead and type out test and then hit enter. Once you see something like this down here, it means the test is completed and everything is working properly. So what exactly are we testing here when we run this command? So just keep that in the back of your mind, and we will revisit that later on in this tutorial. But for now, don't worry about it. As long as you see this, you'll know that things are working properly. So down here, we're still in the package manager in our terminal down here. So to get out of this package manager and just back into the normal Julia REPL, go ahead and hit the backspace key. And now you can see that I'm back inside my Julia REPL at the bottom down here. Let's go ahead and take a look at our first model, and we can go ahead and simulate that model as well. What we'll be looking at today is a lumped thermal model. So on the left side in your file explorer, go ahead and expand the Dyad folder. In there, you'll see a file called hello.dyad. Go ahead and open up that file or select that file. So this is a model representing a simple lumped thermal model using Newton's law of cooling and heating. The specific physics of this model are beyond the scope of today's conversation, but what we are interested in is how this model is constructed and how we can execute and simulate it. So I'll walk over some high-level details of this model right now. So we can see that this component is just named hello. We have a few parameters in this component. We have a parameter representing ambient temperature, initial temperature, convective heat transfer coefficient, surface area, mass of thermal capacitance, and specific heat. So all of these items right here, you can think of them as parameters or constants, in other words, knowns of the system. So these are things that are known that don't need to be solved for. And then at the very bottom down here, we have a variable called T, which is the temperature. And this is the variable that the system will attempt to solve for. Down here in the relations section, we have an initial condition for our T variable. It's specifying that the initial condition is equivalent to T naught, in other words, 320. And then we also have an equation representing the relationships between these parameters and variables. So we have mass times the specific heat capacity times the derivative of temperature is equivalent to the coefficient of heat transfer times the surface area times the difference between the ambient temperature and the actual current temperature. Right down here at the bottom, we can see that we have an analysis named world. This world analysis extends from or inherits from a transient analysis. So world is of the type transient analysis. The model that this analysis will examine is the hello model, as you can see right here. And we also see that this world analysis is parameterized, meaning we can enter in different values for T infinity, in other words, the ambient temperature, and a different value for H, in other words, the convective heat transfer coefficient. If we don't specify these values as we try to execute the analysis, then it will simply just use the default values that you see right here. So let's go ahead and simulate this thermal model and plot the temperature over the course of the simulation. So right down here in my Julia REPL, I'm going to want to make sure I bring my component library into scope. So I'm going to do a using demo components and press enter. Okay, once the component library has successfully precompiled, let's go ahead and simulate it. So down here in the REPL, I'm going to have a variable called result, and I'm going to store the results of my world analysis inside the result variable. So this is how I will call that, and I'll go ahead and hit enter. Once our world analysis has completed, let's go ahead and plot the results of that analysis. So I'll do a using plots to bring in the plots package into my scope, and I will go ahead and plot the result. So we can see here on the right side the results of my simulation. We see that the temperature value begins at a value of 320 degrees, and it asymptotically approaches the 300 degree value. And this makes sense because our initial temperature is specified as 320, and our world analysis specified an ambient temperature of 300. So it makes sense that our model begins at 320 and cools down to 300. Now let's go ahead and interactively modify this analysis. Okay, so like I said before, if I call the world analysis like so, if I call it like this without passing any arguments to it, it's going to assume that my ambient temperature is 300 and my coefficient of heat transfer is 0.7. So it's going to use those default values. However, what we're going to want to do is go ahead and pass keyword arguments to modify these parameters. So what we can go ahead and do here is, instead of just calling world, we will call world, but we will pass specific values for these parameters. So they will not use the default values. Instead, they will use a value of 400 and 0.2. And what I'll do is I'll go ahead and wrap this analysis around a plot call so that we can just plot the results as soon as it's done simulating. So now we can see that the model, instead of cooling down, it is now heating up. And once again, that makes sense because it begins at an initial temperature of 320, but the ambient temperature is actually 400. So it makes sense that our model begins at a value of 320 and it heats up to 400. And that's how we can call our analysis with different keyword arguments and parameters. But let's go ahead, I'm gonna go ahead and switch this plot back to the previous plot, the one where it cools down, because this is plotting the result that we have stored inside of the result variable. So let's go ahead and take a look at some artifacts or what else our result has to offer. So recall that the results variable holds all the simulation results that we got earlier. So I'm going to go ahead and take a look at the artifacts or what other aspects I have inside my result variable. So the first thing I'm going to do is I'm going to do a using Dyad interface, and then I'm going to call the artifacts function and I'm going to pass in result. So it looks like inside of our results variable, we have a few different artifacts that we can access symbolically using these symbols. So it looks like we have a solution plot, solution table, raw solution, simplified system, and initial system. So let's say we want to grab the solution table from our result. And let's say we want to store that inside a variable called table. We would do something like this. We would declare a variable called table, and we would say that that table variable is equivalent to the simulation solution table inside of result. So I'll hit enter right here, and we can see that now we're able to grab a hold of the simulation solution table, just like that. Another thing I want to touch on right here is, recall earlier when we entered the package manager down here and we ran the test command. So exactly what was that testing? So if you go inside of your dot or hello.dyad file, you can see that at the bottom, we have some metadata concerning tests, right? So unit test and test-driven development is essential to software development. So Dyad includes syntax within the model definitions to make it easy to do test-driven development. So when we call that test at the very beginning, what it is doing is running a test case for 10 seconds. And what it expects is that the initial value of our temperature is 320. That is what it's checking for. It's checking for our initial value of T is equivalent to 320. And if that is the case, then it passed our test. And you can see in both our simulations that indeed the initial value was 320. Now what we're going to do is we're going to move on from this simple lumped thermal model, and we're going to go ahead and bring in some other standard libraries to compose our very own component. So what we're going to do is use the package manager to add the electrical components library. So you could certainly enter the package manager and type in add electrical components and hit enter. So you can add it that way if you'd like. Another way to add electrical components is to remain in your Julia REPL right here and do a using PKG, which is the Julia package manager. And once you've done that, enter in the command pkg.add electrical components. So this method will also get electrical components into your environment. Now that the electrical components library has been added, let's go ahead and create our own component. So when we create new components, what we're going to want to do is create them right in here inside the Dyad folder. So I'm going to right click right here and select new file. And I'll just name this file rlc rlc.dyad, rlc.dyad, because what we're going to build right now is an RLC model. We're going to connect a resistor, inductor, and capacitor all together to create this RLC model. The first thing we're going to do is we're going to create a component called step voltage. So I'm going to do a little bit of copy and pasting right here. You can see there that I have a component called step voltage. This step voltage component extends from another component inside the electrical components library. The component it is extending is the 2-pin component. We have some parameters for our step voltage, VF equal to 32, and step time, which is equal to 5. So how this component works is the voltage coming out of this component, if the current simulation time is less than the step time, in other words, if the simulation time is before 5 seconds, then the voltage signature will be 0. However, if the simulation time or the time is greater than the step time, in other words, the current time is greater than 5, then the voltage signature will be VF, in other words, 32. You'll notice that I have not saved this file yet. You can see here by this little symbol, meaning there's changes that have not yet been saved. So I want to show you something right here. Here on the left side, go ahead and expand your generated folder inside of your structure. And in here, you can see there's a few .jl, in other words, Julia files that have been generated for you inside of this folder. Okay, so where does this come from? So what the Dyad extension does is it looks inside of your Dyad folder for any models or analyses, and it generates the corresponding models and analyses in Julia for you, and it places them inside of this generated folder right down here. So if I select Dyad, hello Dyad right here, you can see that this is what we were looking at earlier, the simple lumped thermal model written in Dyad right here. And if I go inside of my generated folder right here to the hello_definition.jl, we will actually see the same lumped thermal model inside of this file, but it is implemented in the Julia programming language using Modeling Toolkit. See here at the top, it says, do not edit this file. And it has this warning at the top of every single one of these generated files. That's because these files are, of course, auto-generated by Dyad. So these are things you can examine, but you don't need to modify, okay? So let's go back to my rlc.dyad file right here. So it looks like we have a component called step voltage, but we don't yet have a corresponding generated file for my step voltage. I need to do is simply save this file. Once I save this file, the Dyad extension will detect any changes over here and generate the corresponding generated files right over here. So I'm going to go ahead and hit save right now. You'll see that this little icon is gone, indicating unsaved changes because I've saved it. And now you'll see that there's a corresponding step voltage Julia file inside my generated folder, which is a model for my step voltage component. So I just want to give you a little insight to that, but we're just going to stay focused on the Dyad code today. So this is a step voltage component. So we're done creating that. So now let's go ahead and create our RLC component. And we will use this step voltage component inside of the construction of the RLC component. So I'm going to do a little copy and pasting right now. And I'm going to go ahead and hit save. Once I hit save, once again, you should see the RLC model inside of my generated folder. And there it is, right there. Okay, so let's take a look at this RLC component and what's inside of it. So it looks like the RLC component has a few different things. It has a resistor, capacitor, inductor, source, and ground. So you'll notice that most of these components are actually just pulling from the electrical components library. For example, the resistor inside of our RLC component is using something from the electrical components library. Specifically, it is using the resistor from the electrical components library. And we're specifying a resistance of 100 for this resistor. We're doing similar things for the capacitor, inductor, and ground. These are all pulling from the electrical components library that we imported earlier. So we're able to use components from the standard library. Also, we can see here that our source is using a step voltage component. And this is simply the component that we just created right up here. So in our RLC component, we are using a combination of components from standard library, but also a component that we created right up here. And down here, we have relations which provide equations that govern our system. So we can see that an initial condition is provided for the current on the inductor as well as the voltage on the capacitor. And we've also connected various components together. And these connections are what enforce physical relationships in between components, right? So we have our source positive pin connected to the inductor negative pin. We have the inductor's positive pin connected to the resistor's positive pin, to the capacitor's positive pin, and so on and so forth. Now that we've constructed our RLC component, what we're going to do is construct an analysis. So our analysis will be called SimRLC. SimRLC. It is extending a transient analysis. We are going to simulate for 10 seconds with absolute and relative tolerances, like so. And the model that this analysis will use is, of course, the RLC model. So I'm going to hit save right here, and inside my generated folder, once again, I'm going to expect to see a SimRLC analysis created inside of this folder. So I'll hit save right now, and there it is. We have a Julia definition for our SimRLC analysis. So let's go ahead and simulate this and plot the results. So right down here inside of my Julia REPL, I am going to type out result is equivalent to SimRLC. Okay, once our simulation for the RLC is completed, let's go ahead and plot the result. So here we can see that the results of our simulation are plotted. We have a signature for the voltage on the capacitor throughout the simulation, as well as the current on the inductor throughout the simulation. So by default, when you call this plot result command, what it plots is the signature or the signals that it had to solve for. In other words, it's plotting the unknowns of the system that it solved for. The RLC does have many more aspects to the model. So let's go ahead and take a look at what else is inside of our model. So here, we're going to have our sys variable be equivalent to the simplified system from the result. So if I go ahead and call this right here, we can see that indeed the unknowns of the system were the voltage across the capacitor and the current across the inductor. But we can, of course, plot other signals. So let's say instead of the current across the inductor, maybe we're interested in the current across something like the resistor. So we can plot that. So the way we would plot that is we would once again call the plot command. We would specify, just like last time, result, because that's what we want to plot. But instead of leaving it to plot its default, what we're going to say is, hey, we want you to specifically plot the capacitor voltage as well as the resistor current. So calling this command, what we'll end up getting is this plot up here. So once again, we of course have the voltage across the capacitor, but now we also have the resistor, because that's exactly what we specified. And that's it. That concludes today's Getting Started section. So now you know how to build some basic components in Dyad, run simulations, stitch together pre-built components for more complex models. And there is much more to learn throughout our Dyad documentation. So I encourage you to spend some time there and going through the rest of the tutorials. Thanks again for tuning in, and have fun with Dyad.